The special weapon that these monster galaxies have is a giant jet array, a jet of its own racing. So the light breaks down into scalar components, right? Why? Because red travels faster through the prism than blue does, or violet does. Why? You can say, oh, well, because at the boundary, the frequency is constant. As a result, the larger wavelengths will travel faster. Not good enough. Why would the larger wavelengths travel faster through the material if you ignore the frequency at the boundary being constant? Right, that's more of a math trick than a real explanation. Obviously, red is moving faster than blue, so the question is why? What's the actual reason for it? What's the physical reason for it? Don't give me the frequency being constant at the boundary. That's for theoretical physicists. That tells nothing about what goes on inside the prism. So what is the interaction between light and the prism that makes the red go travel faster through the material? That's what we are interested in. Furthermore, you change the light source to hydrogen. All of a sudden, you get the 4 speckling lines. Where do we get the 4 speckling lines? From inside the atom. What's going on inside the hydrogen atom? It's going to give you 4 different speckle lines with 4 different colors. How's that working out? Sky is blue, at least we know the reason why, because the blue light is going to get scattered more than any other color, which means that the atoms and molecules making up the atmosphere will have a tendency to scatter blue more than any other color. So why blue? Why not red? Why not green? Why blue? What's the interaction between blue light and the atoms and the molecules making up the atmosphere? All right, so there's a second guy that we need to focus on. I want you to remember this guy. I want you to remember this guy until the end of next week. This guy is important. His name is J.J. Thomson. This guy is not German. This guy is British. J.J. Thomson. Another chance discovery. Man, entire physics is made up of these chance discoveries all over the place, all over the map. What looks like blue light evidently is not light at all, because as soon as you place a magnet near it, this thing gets deflected, which means that it's composed of charges. Not only do we know that it's composed of charges, we also know that it's composed of negative charges. Boom. This is the discovery of electron. The year is 1897. All right. Around the turn of the 19th and 20th century, electron is finally discovered. So what do we know from this experiment? Number one, this beam that you're looking at is composed of negative charges. And then he wins the Nobel Prize in 1906 for this chance discovery. And this guy that we talked about previously, Robert Millikan, is the experimental physicist who actually measures the mass as well as the charge. It's a point particle. It is a point particle. All right, so this is how the electron gets discovered. Okay. All right, so eventually this guy wins the Nobel Prize in 1923, something that we discussed before. So the question is, what is the makeup of an atom? Okay, they try an earlier model, which is called the Plum-Pudding model, which is something that evidently I decided to skip. And then I'm jumping into the model that you guys are kind of born into. So this is the model of the atom, as far as you guys are concerned, that we use in physics. The positive charge is at the center. The negative charge or charges are swarming about the center at a certain radial distance away. Otherwise known as the planetary model that this guy came up with. His name is Rutherford.
Now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy, because if it's mostly empty space, they should pass right through one another. But what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields.
Okay, so a bunch of problems with this model. Number one, the positive charge is concentrated at the center. If it's the hydrogen atom, the electron is going to be half an angstrom away from the nucleus. So you're thinking, what the hell is an angstrom? I'll explain it shortly. Another thing about the hydrogen atom is, I don't know how to explain it. It's like 99.9999% empty space. These atoms are mostly empty. They're empty. They're empty spaces. They're composed of empty spaces. Largely empty space is what you're looking at. All right, so a couple of things about the hydrogen atom. This is the simplest atom known to man. And they knew the ionization energy of the hydrogen atom, and they knew the size of the hydrogen atom through experiments. All right, so this is the ionization energy of the hydrogen atom. This is the amount of energy that you have to supply the hydrogen atom so it gives up its electrons, so it just jumps out. It's 13.58 electron volts. Where did we get this from? We got it from experiments. All right. For some reason, if you're still thinking that physicists come up with these numbers, using solving problems. No, that's not how things are done, guys. Physics is not philosophy. This is experimental science. If we're using numbers, we're using experimentally verified numbers. 13.58 electron volts is something that they knew that this was the ionization energy of the hydrogen atom because that's what the experiments revealed. That's how they knew. Through experiments, scattering experiments, they also could measure the size of the hydrogen atom. This is the size of the hydrogen atom expressed in terms of 10 to the minus 10. This 10 to the minus 10 is known as angstrom. All right, so electron is half an angstrom away from the nucleus, roughly half an angstrom away from the nucleus. So the question is, if atoms are mostly empty space, which they are, why is it that you're not penetrating the chair that you're sitting on? That sounded really obscene. Let's rephrase it. Why is it that you're not going through the chair that you're sitting on? All right, where do we get the illusion of solidness, if that's the case?
Now, how can we reconcile that with the fact that matter is matter, and how the space is empty? What it's filled with is really electric fields.
When the electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now this means that I'm not really sitting in this chair at all. The atoms of my body are about 1 angstrom hovering over the atoms of this chair.
There's a hydrogen atom from your butt, and here's a hydrogen atom from the chair. If everything is made up of hydrogen atoms, obviously that's not true. Notice that the light charges will repel, so which means that this hydrogen atom, this one is going to be repelled by this one, and this distance half an angstrom, so is this distance, so which means that this hydrogen atom is going to be hovering 1 angstrom above the other one. Okay, so what does it mean? Which means that the only force that you experience in life is the electrostatic repulsion. We don't get to touch anything all throughout our lives, and we don't get touched by anything or anyone all throughout our lives, guys. The only thing we experience is the electrostatic repulsion, generating all these chemical reactions throughout our bodies, creating the illusion of contact. So the next time when you guys are feeling lonely, it's the brain's realization that you are really, really lonely in reality. All right, this is what's happening. All right, so the only thing that we experience is the electrostatic repulsion between the light charges. And that's known as the normal force when you're sitting on something.
Rutherford's conception of the atom is a breakthrough, but almost immediately he finds a paradox at the heart of it.
See, the problem was if you've got a nucleus with positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very skewed prediction of classical physics. And that's catastrophic. What it's telling you is that atoms can't exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
What is this guy talking about? He's getting all excited when he's talking about it. The stuff that he's talking about is, oh, is this what happens, this model that you guys are born into? Rutherford's model cannot be the right model of the atom. Why not? Because the electron moving about the nucleus, I don't know, it's accelerating. What happens when a charge is accelerating? I don't know, it causes these electromagnetic waves, right? Where do we get the electromagnetic waves? We get the electromagnetic waves from the accelerating charges. When a charge vibrates up and down, it generates an electromagnetic wave. When a charge accelerates, it's speeding up and slowing down, that's acceleration. It's changing direction, it's an acceleration. When a charge just goes up and down, it generates the electric and the magnetic field components of the electromagnetic waves. So that's what you end up getting. And then when a charge is moving about the nucleus, that's acceleration. The accelerating charges cause electromagnetic waves. So which means that the charge is going to radiate electromagnetic waves. What does it mean? Well, when you're radiating electromagnetic waves, you are losing energy in the form of electromagnetic waves. So the charge moving about the nucleus should lose all of its energy within almost a billionth of a second and collapse into the nucleus. So which means that the model of the atom that you guys are born into is not the model of the atom that we are using in physics. That model doesn't work. Rutherford came up with the model, and just as fast, he noticed that this would not work. They notified the press initially, this is the model of the atom that physicists were using. Evidently, when they wanted to make a correction, no one was interested. And the Disney version of the model of the atom is the one that you guys are born into. Eventually, you woke up to the fact that there's no Santa, but obviously, this is not understood well enough for people to let you know that that's not the model of the atom that we were using. So the question is, what are we using in physics?
One of the key figures in the quantum revolution is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. Only the screams of an ardent fan snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that the budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms.
All right, so Niels Bohr is about to revolutionize science. He's going to become a main competitor to Einstein. And then eventually he's going to replace Einstein in 20th century physics. And he's going to be the founder of an Copenhagen interpretation of quantum theory. That becomes the quantum orthodoxy, in essence. Becomes one of the biggest names in physics history. The year is 1911. He's working with Rutherford. Remember, Rutherford is the guy who came up with the planetary model. He starts working on the theory of the atom in 1911. Spends 2 years working on this theory. And then solves the problem and publishes it in 1913, for which he wins the Nobel Prize in 1913.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom. But Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. We'd have a different orbit, would be stable, would have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
He pulls on Einstein out of his butt in order to solve this problem. Remember, Einstein and his postulates, oh, let's assume this and let's assume that, and let's solve this problem. He comes up with 3 postulates. We will only discuss 2 of them. The third one is not that easy to explain to. You guys are not engineering or physics students, so I don't want to make it that complicated. He knows that the atoms exist. And he also understands that the electron needs to move about the nucleus, or else the electrostatic force will collapse the atom. All right, the electron needs to move, but the electron, while it's moving, it cannot radiate energy. If it did, it will lose all of its energy and collapse into the nucleus. So he said, let's assume that there are these orbitals around the nucleus, within which the electrons can move without losing energy. Right? It doesn't justify it. He says, let's assume, this is called an assumption. Let's postulate that there are orbitals around the nucleus, within which the electrons will be able to move without radiating energy. These electrons cannot exist between these orbitals. They need to be on these orbitals. And as long as they're on these orbitals, they will have to move just like the planets about the sun without losing any energy. And they can jump between these orbitals by absorbing energy and emitting energy. These are known as quantum jumps. So they cannot exist between these orbitals, but they get to jump between these orbitals by absorbing and emitting energy. So notice that this electron absorbs the energy, jumps up to the next orbital, the energy orbital, and stays there for a fraction of a second. And upon jumping down, it releases that energy. That energy gets released. Energy is absorbed, jumps up, energy is released, and then it jumps down to the lower orbital or energy state. Light is coming in this direction, and the light is emitted at a different direction. This is called scattering. So light gets scattered by the sound as a result. So the unit of light is going to get absorbed, which means that the light is quantized. It's a particle. So the particle of light is being absorbed and energizes the electron, and then the particle of light or the unit of light is being emitted. Once again, this works only if you make the assumption that the light is a particle. Publishes his findings in his theory in 1913 and wins the Nobel Prize in 1922.
And that's when the problems became obvious. Being radical, Bohr had gone further, far enough to propose that an electron could exist only in certain orbits, which was contrary to Newton's laws. Then, contrary to Maxwell, Bohr said the electron would radiate or absorb energy only when it jumped between these definite orbits. Those proposals were more than merely contrary. In fact, in the world of physics, they were totally against the law.
Electron is moving about the nucleus. Notice that it makes a transition inward. Color red is emitted. Now it's going to make a transition inward again into the next energy state. This time the color violet is being emitted. It's going to absorb energy in the form of violet, goes up to the next energy state. It's going to absorb energy in the form of red. It's going to jump up to the next energy state.
Bohr's idea that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
This is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake.
Oh, guess what? These guys are skeptics. All right, so they're looking at Bohr's ideas and they're going, I don't think so. They were very dismissive. And these guys are the huge fans of Bohr. So what's the difference between these guys and those guys? It's funny, if you're an art student, these guys are bearded and these guys are well-shaven. Wow, all right, so that's the most obvious difference. From my perspective, these guys are seasoned physicists. And these guys, I don't know what these guys are. I mean, they're just fresh out of their diapers. All right? These guys are looking at Bohr and saying, what the hell is wrong with you, pal? What you're doing is not real physics. You're just coming up with some ideas and you're wasting our time. Why is it that the electron is not radiating energy if it's accelerating? It's proven that it should. I mean, in Bohr's mind, you got these invisible orbitals, and somehow magically the electrons know where they are, and then boom, they stop emitting energy. Are you kidding? I mean, no sane physicist will come up with, well, let's assume that that's the case. No, let's assume not. You can't make an assumption like that when it is already proven that the accelerating electrons radiate energy. You cannot just go, well, let's assume that there are these magical places around within the atom within which the electrons can somehow move, accelerate without radiating energy. Are you freaking nuts? These guys are seasoned. They're looking at Bohr like, why are you wasting our time? Pal, this is not real physics. This is like Disney World before Disney was even born. And how does the electron know where these orbitals are? How does it know how to get up to the speed or slow down? How does that magic happen? No explanations, absolutely no explanations on the part of Bohr. He says, he pulls an Einstein out of his ass. He says, hey, I don't want to argue. Let's assume that these are correct, but let's check to see if we can solve this problem making those assumptions. All right, he follows in Einstein's path 100%. He says, just put aside your experimental results, put aside your common sense. Just go along with it. Let's check to see where we land. That's what he says, in essence. Here's where he lands at the end. R represents the radius. It gives you the locations of these orbitals inside the atom, these energy orbitals that you're looking at. R1 is the first one, R2 is the second one, and the third one. And the weird thing in the mathematics is these orbitals will be located to Planck's constant. Pi is going to matter, so this is also a constant. It's an irrational number. K, the strength of the electrostatic force is going to matter. M, the mass of the electron is going to matter. And the charge of the electron is going to matter. The location of these orbitals are related to the constants of nature. There are 20 plus constants. And these are all finely tuned numbers. If you vary these numbers just a little bit, this universe would have never formed. All right, we live in a finely tuned universe. So the question is, who tuned these numbers so that there would be a universe eventually yielding life, resulting in life in this universe? Okay, so that's an argument, that's a discussion that we will have next week. Let's get back to this one. It's a combination of a bunch of constants. All right, so when he did the mathematics, this is the result of the mathematics that he came up with. So the question is, will it give us the hydrogen atom? First orbital is going to be located here. This would be the size of the hydrogen atom. If this formula is correct for the hydrogen atom, we should get half an angstrom. We should get 0.53 times 10 to the minus 10 meters. All right, so these are a bunch of constants plugged into a formula that Bohr came up with. Right on the money. Right on the money. Experimental and the theoretical numbers match with 100% accuracy. So that's one prediction, which is verified by experiment. These orbitals are known as the energy orbitals. All right. So once again, the formula that he came up with looks like this. N represents the first one, the second one, the third one, and is 1, 2, 3, and 4. That's what you're looking at. Once again, the energy of the orbital is determined by exactly the same constants, the constants of nature. For the hydrogen atom, the energy of the first orbital is the ionization energy of the hydrogen atom, which is 13.58 electron volts. So you plug the numbers in, and then you come up with 13.58 electron volts. Once again, the experimental and the theoretical numbers match. So what does that mean? That means that the theory is good. How's that? We don't debate things in sciences. It's not like philosophy. It's not like religion. It's not like politics. You got a theory, it needs to be expressed in the form of math so that it makes a prediction that we could test to prove or disprove a theory. The seasoned physicists not agreeing with Bohr had no bearing on the results whatsoever. The fact that Bohr had no explanation as to how this was possible had no bearing on the results of this experiment either, on the results of this theory either. We came up with some assumptions to make it work, and which means that his assumptions were correct. There are orbitals inside, energy orbitals inside the atom, within which the electrons are moving without radiating energy. Is it that they're not radiating energy? Who knows? There's no explanation for it. How does an electron know how fast it goes? When it's near that orbital, how does it know which speed to get up to or slow down to? No explanation for it. It simply does. Electrons just simply do. Because the experimental and theoretical numbers match, that's it. That's all you need. Theory is good. It's proven to be correct. And another verification that the light is a part of it. There's the lowest energy state, M1, the energy state of the first orbital. There's the energy state of the second orbital. These are known as the excited states because the electron needs to be energized to get up to these states. There's the third one. Here's the fourth one. Here's the fifth one. All right, so the electron is going to grab a unit of energy of a photon to jump up to this one, and then grab a photon whose energy is going to match the energy difference between this state and that state, and so forth. The electron jumps up here and then remains here for a fraction of a second, and then jumps back down to the ground state, the lowest state. All right, so this is the difference between the energy states, and the difference between the energy states has to match the frequency of the quantized photon that you're looking at. All right, so now you can provide an explanation for why is it that you have red, why is it that you have blue-green, why is it that you get 2 shades of violet from the hydrogen atom. Explanation becomes fairly easy. Remember in the Bohr's formula, when n is 3, you end up getting red, 4 blue-green, 5 and 6 you end up getting violet. This is so happens the reason we end up getting that is because, look, when there is a transition of the electron from the third energy state to the second one, color red is emitted. N is 2, N is 3. When the N is 3, you end up getting color red. When N is 4, you end up getting blue-green. 5 and 6, in the Bohr's formula, you end up getting 2 shades of violet. Evidently, N represents the energy state of the orbital.
The agreement between Niels Bohr's model and the experimental measurement was nothing short of amazing. Like Newton's idea of action at a distance, Bohr's model of the hydrogen atom was accepted not because it was easy to grasp or comfortable to live with. Instead, like Newton, Bohr provided compelling agreement with observation that couldn't be denied. Nobody knew why Bohr's model of the atom should work, and yet the best minds agreed that it did work. Why? Because in Bohr's physics, like Newton's, there's an agreement between theory and experiment that is quite simply too precise to ignore. Niels Bohr took the old physics, and with his profound insight into the atom, propelled it directly into the future.
All right, so wins the 1922 Nobel Prize for his paper on the hydrogen atom. All right, so this is his picture on the Danish currency, so he's a huge deal. The other thing that he explains and does a really good job in explaining is the scattering. Why is it that the blue light gets scattered more than any other color?
Electrons exist in an orbit or energy level around the atom. Under normal circumstances, these electrons remain in their lowest energy state, the ground state. If those electrons are stimulated by some form of energy, could be visible light, could be heat energy, it can be ultraviolet energy, whatever the case may be, these electrons become excited.
One way is to have some other atom come and bump that electron up into the next level. Okay, that's one way. Another way is if a photon of just the right energy comes along, that electron can absorb that energy and just take that photon out of existence, and it goes up to the next level, having basically eaten that energy.
That transition lasts for maybe a millionth to a billionth of a second. The electron then will make another transition back down from a higher energy level to a lower energy level. When that occurs, the electron must release the amount of energy it had acquired to make the transition upward. When it makes the transition downward, amidst this amount of energy, this photon of energy, a spectral line is produced.
Now this is very interesting actually, because suppose a photon of the wrong energy comes along. Suppose it's sitting here on the ground state and it wants to go to the first excited level, and a photon comes along that doesn't have enough energy to lift it up. Well, then it can't absorb that. It could try, but it just wouldn't go anywhere. So that photon can then just go right through. It won't get absorbed, and the atom will sit there in its ground state. Suppose a photon comes along that has too much energy that actually would make it go between, say, not to the first excited state, but somewhere in between. That photon will also just pass through because it would leave the thing in a wrong spot. So it's only certain photons that can actually be absorbed. Of course, once it's in the first excited state, it could then receive another photon to move it to the third or the fourth excited state.
Depending on the level of the transition, how far that electron jumps from a higher energy level down to a lower energy level, that electron may emit visible light, may emit ultraviolet light, infrared light, X-ray energy, it all depends. But whatever is emitted, the energy emitted is unique to the atom and hence the element.
This is the clue for discovering what atom is there, or one way of finding out, because each atom has a unique set of
violet energy.
Two electron can absorb that out of existence, that electron energy, and just take that photon out of.
Okay, notice that the blue is coming in. Good. Now the atoms and molecules making up the atmosphere, their energy states are just such that the energy orbitals are such that the difference between the energy orbitals is going to match the quantized blue line. All right. As a result, the electrons will become excited enough to jump up to the next orbital. They will stay there for a fraction of a second, and upon jumping down, they will release that blue color. And when they do, it's going to get released in a different direction. So that's known as scattering. Guys, understand in the background, you have the black light radiation curves. All right. So if the incoming light, the quantized light, the photon of light, if it doesn't have the right amount of quantized energy that matches the difference, energy difference between the energy orbitals, it's going to go right through. It's not going to get absorbed. It's not going to get re-emitted. It's just going to get ignored completely. All right, so the atoms and molecules making up the atmosphere got their energy orbitals just so that they can absorb and re-emit blue light more than any other color. All right, so the violet is coming in, it's going right through because they quantized or the photon of violet photon is not, it doesn't have the right energy that matches the difference in energy levels of that atom that you're looking at. All right, so what's happening is the energy is being absorbed, the electron jumps up and it stays there for a fraction of a second, and upon jumping down, it releases energy. All right, so this is known as a quantum jump. And this absorption and remission is what slows the light down inside these optically dense mediums. All right, so what's happening here within the prism? Red is moving faster through the prism than blue. Blue is moving faster than violet, and which means that the transition for red is taking place a lot faster than the transition for blue or violet. So the question is why? We can get the answer very easily. Look, guys, the red is being emitted when there's a transition between the third and the second energy state, and then the blue is going to get emitted. Blue-green is going to get emitted when the transition between fourth and the second. All right, so the violet, it takes even longer. This is a much bigger transition. All right, because the transition is shorter, this takes less amount of time because the transition longer. For blue, it's going to take a little bit longer. For violet, it's going to take even longer. And that's the reason why light separates.